In this screencast, I want to do an analysis of the performance of Mergesort. That is, I want to compute its asymptotic performance. So here's a sample of a version of Mergesort. And in this particular version, what happens is we have an array that we're going to sort. And what we do is we copy the front half of that array into an array B, the back half of the array into an array C. And you'll see why in a second. Then we do merge sort on the front half of the array and merge sort on the back half of the array, and finally we merge those two. And I'll talk about the merge operation in a second. So what's going to be the basic operation for this? Well, we're going to be mostly concerned with comparison. So we're not going to worry about these copy operations. So this is a typical recursive implementation of merge sort in the sense that there's two calls on half of the list and followed by a merge operation. So let's look briefly at the merge operation so you can remember what the performance of just this piece of the code is. So here's merge, and again what it's going to do is it's going to take our sorted, now this array is now sorted, this array is sorted, and we're going to put the resulting answer into A in such a way that it will now be sorted. So how does this work? Well, just think of these two lists, and what you're going to do is compare the elements, start at the smallest elements in each one, which would be at the 0 spot, assuming we're sorted in ascending order. And we're going to compare those two, and whichever one is smallest, we're going to put it in A. And so that's this comparison here. Choose the smallest one. If B is smaller, we're going to put that into A. Otherwise, we're going to put C into A. And when we do that, we have to update the indices that point to the appropriate elements in B and C. We'll just update one of those, of course, and then update the index for the array A. So if you think about this for a second, A contains P plus Q elements. So in the worst case, neither list will get exhausted, so we won't drop down into this part, which just does a copy. And what will happen is that we'll stay in here and we'll have to do a comparison for all P plus Q elements. So what this means is that the merge operation is going to be linear because there's going to be P plus Q comparisons. It's going to be linear in the size of its input. The size of its input is basically P plus Q. So, all right, so now we're really in a position to analyze merge sort. So let me just review some of this. Since it's a sorting algorithm, the input size is going to be characterized by the number of records to be sorted, so we're going to call that N. The basic operation is going to be key comparison. We're going to assume that the copies are much faster than the key comparison, so this is going to be the operation that we need to worry about the most. We're going to analyze the worst case. In the worst case, its major impact is going to be when we're doing the merge operation and where the lists are exhausted only when both have a single element left in them. Now here's the key thing to notice. If you go back and look at the merge sort code briefly, if you go back to that point in the screencast, you'll see that the merge sort routine involves two recursive calls to merge sort on lists of half the size. So that's where this comes. This is the two calls calling merge sort on a list of half the size. Plus this n comes from the merge operation. And we're going to assume, even though it's not exactly true, that the number of key comparisons that needs to be on a list of size 1 is one key comparison. That's not actually correct, but it makes the math a little bit easier to understand what's going on, and it's not going to make any difference in terms of the asymptotic performance. So in this slide, this is where we're going to use back substitution to get a closed form solution for the performance of merge sort. Now remember, that's what we want. The recurrence relation that describes the number of operations, That's fine. That gives us a lot of information about what's going on and intuition about what's going on. But it doesn't tell us in a closed form way, in other words, a way that's easily computable, how many operations that it's actually going to take to sort a list of size n. So here's what we do. We apply the recurrence relation. So this is the recurrence relation when the list is of size n. And then here's sort of the key step. The second step is the key step to understand. What we're going to do is apply it again, but now we're going to apply the recurrence to n over 2. And so when we do that, this is the recurrence relation applied now when the argument to merge sort is of size n over 2. This is the number of operations that the recurrence relation says it's going to take. In other words, we divide the list again in half, so now each call to merge sort is only going to be working on a quarter of the list. There's going to be 2 calls to that, and then the merge operation is going to require n over 2. So now let's multiply this out. So the 2 times the 2 gives you 2 squared here. M of n over 4, this is the number of comparisons for a list of size n over 4. We can think of that, and you'll see why in a second we want to think of it this way, as m of n over 2 squared. And then multiplying this 2 times this gives us another n, and then adding that n gives us 2 times n. So now we do the same thing over again, but now we apply the recurrence relation to m of n over 2 squared. And when we do that, we just bring down the 2 squared. This m of n over 2 squared, now by applying the recurrence relation, we get this piece. And then the 2 times n just comes down here. So now what we need to do is multiply this out. This is the recurrence relation that we have for m of n over 2 squared. And when we multiply it out, we're going to get 2 cubed, m of n over 2 cubed, plus 3n. Again, there's 4 here, times the n over 4 gives us another n. So think about that and make sure you see the pattern, see what's going on. This is increasing by 1 every step you take. This is increasing by a factor of 2 every step you take. And this denominator is increasing by a factor of 2 every step you take. So after a total of k substitutions, we're going to end up with, this is equal to 2 to the k times m of the list of size n over 2k, 2 to the k, plus k times n. So make sure that you pay close attention to the last slide and understand where this comes from. So this is after k steps of back substitution. Now, what we want to do, of course, we've seen the pattern, and now we want to get this to the base case so that this is no longer a complex formula, it just becomes some number. And so where is that? That's m equals 1. And so to get this argument here, n over 2k, to be equal to 1, what do we have to do? Well, if you multiply both sides by 2 to the k and then take the log, you see that k must be equal to log of n. So now if we plug log n into that formula for k, remember the point here is to get us down to the base case of m of 1. What you get is, so we've got log n steps. So you get 2 to the log of n times m1 plus k, which is log of n, times n. And you can simplify that. 2 to the log of n, of course, is just n. So basically what you end up with is n plus n times log n. So by ignoring this smaller term, we end up with that this is big theta of n log n. And that's the worst case for Mergesort. We'll see later in the course, and I'll do a screencast on it, that there's a simpler way to do all this in terms of we just apply a theorem that's called the master theorem, that allows you to analyze divide and conquer algorithms such as Mergesort just by applying the theorem. But that's a story for another screencast.